Scotty, and this is my Lab 5 on the Fallen Slinky. Alright, introduction. So the purpose of this lab is to predict the motion of a falling Slinky that we will get from a video. So as always, the software that we're going to be using is Tracker to observe the motion. And in this lab, we'll be comparing that to a computational model, which of course we're going to use GlowScript. And the purpose of this is determine if the bottom of the Slinky will stay stationary or move, and compare that with the tracker data. So overall, like what our findings were was there were some differences in the motion between the model and the actual like motion from the video, but they kept like pretty similar. So the fundamental principles that we'll be using is Newton's second law, which is change of momentum is equal to the applied force. You rearrange this to get the velocity update and the position update formulas, which we're all familiar with. As well as that, there'll be a couple of other forces we're looking at. The drag force, which is the resistant force caused by the motion of something through the air. So as the Slinky's falling down, you'll have the drag force working up against it. You also have the Slinky force, which in this case will be a tension force. And then finally, the force of gravity, which works in the opposite of the tension force. And that's F equals mg. So this is our observed motion. It was from this video on the right, where you sit there and you drop the Slinky until it hits the ground. As you can see, this is what it looks like over here. And our mass was 0.218 kilograms. Our starting height was the total height was 1.7 meters. And so this is our initial position, this vector right here. And our initial velocity, of course, is 0 since we started dropping it. So this is the coding. These are the initial conditions. Basically, all this was plugged in from what we got from Tracker. So the ball mass, the initial position vector, the initial velocity vector, your gravity, yeah, and then also your drag force constant, which is equal to 75 for one round, and then 0 when the model is gravity only. So that's this first part of the code is where there's 0 net force. And this is because the only forces acting are your gravity and your tension force. So what that'll do is you'll calculate your forces here, which should be equal to 0. And then you'll do your velocity update and your position update using your net force. So that is why in this case the bottom of the Slinky does not change position, and that's because there's no net force. However, in this loop, we add the drag force into the equation. This makes it so there is now a net force. And that's because you have the drag force added, so it's not just the force of gravity and the tension from the Slinky canceling each other out. And you'll see that in the graph. So this is what our results showed. Like you have obviously the area where it's just the tension and the force of gravity, so you have 0 net force. And then you see once the drag force gets added, the position starts to change. Overall, they were really close, the predicted and observed. So that means the model is good. There were a few possible errors that could have occurred. Obviously, when using Tracker, there could be like inaccurate placements when you're tracking the object. So it's very easy to make a mistake there. Also, there can be like other outside forces not accounted for by the model, like the drag force, force of gravity, and the tension force aren't the only thing that could be acting on the Slinky. So as mentioned earlier, the bottom of the Slinky remains stationary because the forces in the y direction cancel out. So that's gravitational force and tension force. And then it's what if there's a large weight attached to the end of the Slinky, would it change? It depends on how much the weight weighs. Because if the weight is enough to make the gravitational force stronger than tension, it would not remain stationary. So the net forces wouldn't cancel out. That's it. Thank you.